Since the beginning of nuclear warfare in World War II, a Navy ship has never come under nuclear attack, nor employed its own nuclear arms. But history does not guarantee the future. A nuclear weapon could be detonated at sea anytime, tomorrow, next week, next year, or now. A nuclear war, a Navy ship, your ship, alone on the high seas. What can you expect? What effects will the detonation have on you, on your ship and its fighting ability? What effects will your weapons have on the enemy? Questions, important questions that you must be able to answer. For even if you don't believe a nuclear attack will ever happen, you must believe that it could. But you may be thinking that nuclear weapons are too complex and their effects too many to be understood. Each weapon produces blast, thermal radiation, and nuclear radiation, three phenomena which have a range of effects. Yet, you need not know all the details in order to maintain your ship's fighting ability or gauge the effect of your own weapons. Certain basic facts are enough. For convenience, we'll divide these facts by burst height, keeping in mind that these divisions are somewhat arbitrary. Now let's start with high-altitude bursts of the megaton range. The most significant phenomena is that nuclear radiation will produce widespread disturbance of the ionosphere, the region between 25 and 250 miles altitude. Radar and radio wave propagation will be affected, and consequently, your communications will be affected. It will suffer attenuation, interference, and distortion to some degree, and may even be seriously degraded for an indefinite period. High-altitude detonations may also affect satellite communication, especially when the intense ionization region intersects the relay circuit path, or the satellite itself is damaged by nuclear radiation. Another phenomenon produced by nuclear bursts at high altitude is the electromagnetic pulse, or EMP. Although the physics behind EMP are complex, the results are clear. It produces induced currents and voltages that can damage electronic equipment. Detonations above 130,000 feet produce EMP effects on the surface over areas that may encompass thousands of square miles. Blast from high-altitude detonations is not usually a serious factor for ships at sea. It decreases at about 100,000 feet, until at 150,000 feet, it is 20 to 40% of what it would be at sea level. Thermal radiation, however, is another story. The heating effect on the surface may be significant, and the visible light emitted is a great hazard. Even at considerable distances, it can produce flash blindness and retinal burns if viewed directly. Air bursts, defined as detonations where the Earth's surface does not modify the effects, can cause blast, thermal radiation, ionizing radiation, and EMP damage. Also, it is potentially the most hazardous to the ship's company. Ship impairment is usually stated in terms of seaworthiness, mobility, or weapon delivery capability. Blasts from airbursts where overpressure exceeds 10 psi can cause substantial damage to destroyer-type ships. Above 14 psi, it could even result in hull rupture, flooding, and sinking. A multi-megaton explosion broadside to the ship might cause roll to the point of capsizing. The shock imparted by blast to the superstructure can damage or carry away equipment. At greater distances, overpressure above 6 psi can distort, rupture, and carry away light structures and equipment with the possible loss of weapon delivery capability. Interior equipment and compartments may be damaged by the blast, collapsing deck structures or bulkheads. Overpressure entering through openings can damage boilers. Blast injuries to exposed personnel, represented by this dummy, is usually severe over 3 psi. Here it was 6 psi. Injury results from crewmen being thrown against the deck or structures and by flying objects. Blast injury is increased in nuclear detonations because of the short rise time of the shock front. A short rise time is somewhat analogous to the force exerted by a baseball bat as compared to that of a football blocker. Although there is no direct data on the effect of blast on unexposed persons aboard ship, it can be surmised that in crowded spaces, such as CIC, injuries would result from collapsing bulkheads and flying debris. The latter can be an acute problem where loose gear is not properly stowed. Depending on your location, overpressures as low as 5 psi can rupture eardrums. Loss of hearing by key personnel would severely handicap damage control operations. The effect of nuclear blast on vulnerable flight deck aircraft could be severe. Blast wind and overpressure could cause direct damage to structural members and indirect damage as planes are pushed into each other and overturned. The second airburst phenomenon that affects surface ships is the thermal radiation preceding the shock wave. Such topside structures as the supports for radar antennas and masts may be weakened. Light metals such as aluminum might be melted. The surface of antennas could be charred and the bonded plastic surface ablated, thus reducing electronic frequency transmission. On most combatants, there is insufficient combustible material topside to sustain a fire ignited by thermal radiation. The exception is the carrier, which may have flammable liquids, ordnance, and other combustibles on the flight deck. A fire such as this one, which was caused by an accident, could result from thermal radiation, putting the carrier completely out of operation. With the exception of carriers, thermal radiation will rarely affect the ship's seaworthiness. However, by weakening structures, it may increase the range at which blast can disable a weapon control system. As the casualties in Hiroshima and Nagasaki showed, the effect of thermal radiation on exposed persons is a very serious concern. Flash burns may be sustained at distances where blast and nuclear radiation might not produce injury. Burns from thermal radiation run the gamut from 1st to 3rd degree and are similar in many ways to burns from fires. They can result from direct exposure, from clothing catching on fire, or from fires started by the thermal radiation. One difference in the thermal radiation phenomena is that the energy is concentrated in a few millisecond pulse. To give you an idea of the tremendous heat produced by a nuclear burst, consider the following rough comparison. In a period of just a few seconds, a target 2½ miles from a 1 megaton detonation will receive almost the same amount of radiant energy as the sun delivers to a location along the Earth's equator in 1 hour. Another difference in thermal radiation from nuclear weapons is the pattern of the body areas affected. For devices of 100 kilotons or less, burns will occur primarily on the directly exposed parts of the body, unless the clothing is ignited. Also, 1st and 2nd degree burns from these low-yield weapons would involve limited areas and occur only on the side of the body facing the burst. Severity of burns, however, is not the only factor related to the effectiveness of the crew. Such personnel as gunners and the bridge watch could be seriously handicapped by even 1st or 2nd degree burns on hands or by burns around the eyes, producing swelling. Taking shelter behind any substantial opaque structure will help reduce injury from flash burns. Even when this is not possible, covering exposed parts of the body will help. Eye injury, flash blindness, which is temporary, and retinal burns, which are permanent, are extreme hazards, even when the fireball is at a great distance. The reason is that the optical process of image formation within the eye negates the inverse square law and keeps the intensity per unit area on the retina a constant, regardless of distance. An example is that a 1 megaton explosion at a height above 130,000 feet can produce retinal burns as far as the horizon on a clear night. The only sure means of negating these effects is to avoid looking at the burst and shielding the eyes. The third phenomenon associated with an airburst, nuclear radiation, is the only effect unique to nuclear weapons, and in some ways is the most dangerous. To appreciate its effects on a ship's crew requires a brief description of the way gamma rays and neutrons affect the human body. After the discovery of X-rays toward the end of the last century, it became increasingly clear that there was an element of danger associated with exposure to ionizing radiation. Within living tissue, it alters and destroys some of the cell's constituents. Also, the products formed may act as a poison. The general term given to these changes is radiation sickness, which can range from mild discomfort to total incapacitation and ultimately death. Radiation sickness usually has three phases: initial, latent, and final. Their duration and severity depending on the radiation dose. During the initial phase, crewmen may experience nausea, vomiting, headaches, dizziness, and a general feeling of illness. This is followed by disappearance of the symptoms, the latent phase, in which crewmen will be able to perform most duties. The onset of the final phase is marked by frank illness, requiring hospitalization for high doses. At present, there is no way of modifying the effects of nuclear radiation after exposure, and so the crew must take cover prior to the burst. However, since gamma rays and neutrons have high penetrating ability, shielding adequate for thermal radiation will be insufficient. Only specially hardened spaces or compartments below the waterline can be considered safe. When discussing the effects of airburst nuclear radiation on communications and fire control systems, two categories must be considered. First, the damage inflicted directly on the electronic components, and second, the effect of ionization on the propagated signal. There are three types of failure modes associated with electronic equipment: ionization, displacement, and thermomechanical shock. Now, it is not necessary to explain each of these, except to point out that it is difficult to predict the level of semiconductor damage. Likewise, it's difficult to foresee the effect of electromagnetic pulse, EMP, on a particular piece of electronic equipment. However, as with high-altitude bursts, the airburst EMP can cause serious damage, although not over as wide an area. Due to ionization, the propagated signal may also undergo absorption, interference, and distortion, ranging from minor to a complete blackout. Inasmuch as many weapons also depend on electronic systems, both in the missile and fire control system, the effect of nuclear radiation on these can be serious. Missile systems are, of course, subject to other types of damage besides ionization. However, here again, system design so influences the amount and type of damage that no predictions can be made. Also, the position of the weapon, in the magazine, in transit, or on the launcher, must be considered. For some missile systems, the vulnerability of the radars and guidance illuminator can be a major factor, perhaps more critical than missile or launcher systems. Surface bursts, those that interact with the water, differ only slightly from air bursts. First, a large volume of water will be vaporized and carried up into the radioactive cloud. For example, it's estimated that if 1% of the energy of a 1 megaton weapon is expended in this manner, about 20,000 tons of water will be converted into vapor. That is approximately the same amount of water as in 240 average-sized home swimming pools. When the cloud reaches high altitude, the vapor will condense into droplets, and after sufficient cooling, fission products and residue become incorporated. Gradually, the droplets fall back to the surface over a large area, depending on atmospheric conditions. In general, however, radiation from fallout produced by a surface burst at sea is not significant. Underwater bursts. The phenomena associated with these have certain common characteristics, which can be modified by the yield, depth of explosion, and area of the water body. However, for the sake of description, we will divide the effects into just two categories, underwater and surface. The rapid expansion of the gas bubble formed by a nuclear underwater burst results in a shock wave being sent out in all directions. Compared to air bursts, its peak values are much higher for the same distances, but the duration is much shorter. For example, the peak overpressure from a 100 kiloton burst at 3,000 feet in water is about 2,700 psi, compared with a few psi for an air burst. In deep water detonations, the rising hot gas bubble will expand and contract, producing multiple shock waves, which are reflected from the bottom, surface, and ship's hull. Also, although the shock reflected from the bottom may be lower in pressure, it arrives at a steeper angle, and therefore may induce more damaging motion to the target. The impact of a shock wave on a ship is a sudden blow, like a high explosive blast, except nuclear bursts act over the whole ship instantaneously. There are two types of effects that can be expected. First, the direct shock to the hull, and second, the indirect effect resulting from components within the ship being set in motion. With shallow water bursts, boilers and main propulsion machinery will suffer heavy damage. As the range increases, light interior electronics will still be affected, even at distances where there is no hull damage. If the vessel is underway, machinery will probably suffer somewhat more damage than if at anchor. On the surface, an underwater burst will push up a plume or spray dome when the hot gases vent. As the column or plume subsides, a donut-shaped ring of mist is formed, similar to the spray at the base of a falls. This is the highly radioactive base surge. After a short time, the water droplets in the base surge evaporate, leaving fission debris suspended in the air. This invisible base surge continues to move with the prevailing winds and can be a considerable radiation hazard to ships encountering it unawares. High altitude, air, surface, and underwater detonations. This film has touched on some salient effects of each of these in an ocean environment. It's far from exhausting the material available. However, being aware of even these introductory facts is critical. For regardless of your duty aboard ship, a nuclear detonation will affect you to some degree. Knowing how and to what extent is the first step in dealing with a nuclear attack. Likewise, knowing how your weapons will affect another ship will help maximize their effectiveness. Of course, there's no way to know if you will ever need this information. But considering the weapons involved, this is too big an if to leave to chance.